So today we are going to talk about inverse trig derivatives. It'll be very short. This is actually our last section in Unit 2. Okay. Next week, if you look at our schedule, we have 3 days of in-class review, which will include multiple choice problems, free response problems, and of course a review. I am going to go ahead and give you the review today in case anybody needs to get started on it this weekend. Okay? Our test is Thursday and Friday. Okay. So, in pre-calculus, last semester, you talked about trig functions and you talked about inverse trig functions. Okay? Let's look at y equals the sine of x. Does this pass the horizontal line test? Which means what? Doesn't have an inverse, okay? But it does have an inverse, okay? What we've done in order to let y equals sine of x have an inverse is we restrict the domain to negative pi over 2 to pi over 2. Now does this pass the horizontal line test? Okay? So this is y equals sine of x, and you have that on your paper, right? When we reflect this about the line y equals x, or if we take all those coordinates and we switch x and y, we get this graph, okay? Where in y equals sine of x, our domain was negative pi over 2 to pi over 2. In the inverse, now our range is negative pi over 2 to pi over 2. Okay? X's and y's switch. Domain and range switch. Y equals sine of x. We know that range is negative 1 to 1. That becomes our domain for the inverse. Okay? So you'll see here I wrote this as x equals sine of y. Okay? We switch x and y. There are 2 different ways to write inverse sine. We either write it as this, or we write it as y equals sine inverse of x. Okay? You are going to see more of the arc sine of x in your calculus problems than you will sine inverse, but you need to be able to recognize both of them. Okay? Y equals cosine of x. Does that pass the what did I do? That's not right. Y equals sine of x. Does that pass the horizontal line test? No. Okay? It does not pass the horizontal line test. So it didn't show up on your paper, but it's showing up here. In red, I've highlighted, we restrict the domain of y equals cosine of x to 0 to pi. Therefore, if we take that red chunk and plot the inverse, we get this. Y equals our cosine of x. And then we have to do the same thing for tangent. What does tangent of x look like? Okay. Remember with y equals tangent of x, okay, we have these squigglies, for lack of a better word, that repeat over and over and over. We have asymptotes that are pi apart, that start at pi over 2, 3 pi over 2, etc., etc. Okay? Well, if we have all of those squigglies, it does not pass the horizontal line test. But if we only take one, this one here, between negative pi over 2 and pi over 2, and then we take the inverse, we have that. Okay? So we had a range of all real numbers for tangent. Now for inverse tangent, our domain is all real numbers. Whatever the range is in the original becomes the domain for the inverse. Okay? And since we restricted our domain to negative pi over 2 to pi over 2, oh no. Please make this correction with your pencil. What did I do wrong with my domain? These should be parentheses. I got in a hurry and I just did some copy paste. Those should be parentheses because we have those asymptotes. We can't actually include those. Okay. So our range for the inverse tangent is negative pi over 2 to pi over 2. So you'll see on the back side of your sheet this. Okay. This gives you the domain and range for all of the inverse trig functions. Okay. You worked very closely with arc sine, arc cosine, and arc tangent last year in pre-calculus. I'm not super concerned about you knowing the domains and ranges of all of these, okay, but you need to understand where they come from. Now, the calculus side of it. Okay, what I'm going to do is we are going to come up with what this derivative rule is, and we can do the same for all 6 of these inverse trig functions, but we're just going to do it for inverse tangent. You know that this is how we will find the others, but then we're going to write down all the rules and remember those rules, okay? So, y equals tangent inverse of x. What does that mean? Okay. If we use our switching x and y, right, this just means tangent of y equals x. Do you agree? Okay, because it's the inverse of y equals tangent of x. So we switch x and y. X equals tangent of y. Okay. Now, let's take the derivative of this with respect to x. What kind of function have we written here? Implicit, right? So what's the derivative of tangent of y? Secant squared y. Good, dy dx. Equals, what's the derivative of x with respect to x? 1. So dy dx is 1 over secant squared y. We can divide that over. Which is the same as what? 1 over secant is the same as cosine. So 1 over secant squared is the same as cosine squared. Okay. Now, do we want a derivative rule in terms of y? That is not going to be helpful. Okay. So here is our trick to write it in terms of x instead. Trig means the study of which shape does triangles. Trig means the study of triangles. Okay? We have a triangle where y is our angle. And the tangent of y is x, or x over 1. Right? Our tangent ratio is x. Our tangent ratio means opposite over adjacent. So x over 1 is our opposite over adjacent ratio. Okay? I just took tangent of y equals x. Y is our angle. Opposite over adjacent needs to be equal to x. What does that mean about our hypotenuse? Almost. No. Good. So we have radical x squared plus 1 squared. Right, you? Okay. So now we have cosine of y squared. Cosine of y. Well, if y is our angle, cosine is adjacent over hypotenuse. Right? Good. adjacent over hypotenuse. So we are going to write what? 1 over the square root of x squared plus 1 squared. This is the cosine ratio squared for cosine squared. Let's see. In that box of rules, find inverse tangent. This is the rule that you need to remember. The derivative of inverse tangent is 1 over x squared plus 1. Using our knowledge of inverses, implicit differentiation, and our knowledge of triangles, we could do this for every single inverse trig function, but we are not, okay? Because this isn't what I want you to focus on. What I want to focus on is how to take these derivatives using the rules, okay? So you've already come over here to, oh, I've written it in for you. I forgot that. Inverse tangent derivative is 1 over 1 plus x squared. I'm going to give you a moment for you to write these down on your note sheet. You should see a little bit of a pattern. Okay, now this is a lot to remember, okay? In your homework, you will see all of these different derivatives. On your test, these are the 3 that you'll want to focus on. Those are the ones you'll need to remember. What's nice, inverse sine and inverse cosine have very similar derivatives, okay? Inverse sine and inverse tangent are the 2 that you'll see on the AP test. Okay, so those are the 2, those 3 are ones we have to remember. Inverse sine and inverse tangent are the ones that are most popular out of those 3. Okay, so when you're doing your homework, you can reference this sheet for arc cotangent, arc secant, and arc cosecant. However, by next Thursday, you're going to need to know arc sine, arc tangent, and arc cosine off the top of your head. Okay. So let's practice some derivatives. We have 4 examples, and they're written there for you. So our first example is the derivative to y equals arctangent of 2x. Okay. So as a side note, we wrote down this rule. Okay, don't write this down, you already have it. I'm just putting it up here for us to see up at the board. So if we take the derivative, dy dx, we have 1 over, what's going to go here instead? Since 2x is inside arctangent, we want 2x squared here. And since 2x is inside arctangent, we have to multiply by 2. So our derivative is 2 over 4x squared plus 1. Questions? Very nice. Okay. Example 2. Just so we can have it to reference up here. Okay. Here's our derivative rule for arc sine. Okay. Now, when we look at these rules, since x is inside, this is x squared. Whatever is inside our function, that is what we put here. Okay? So, since we have radical x inside, this becomes 1 over square root of 1 minus radical x squared. Are we done? Isaac, why are we not done? This is true? Is that the only reason why we are not done? We're going to leave the radical in the denominator. We're not going to worry about that. What did you say? What do we have to take the derivative of? Square root of x. We need to multiply by the chain rule. Square root of x is inside our function, so we have to multiply by its derivative. Remember, square root of x is like x to the 1/2. So we're going to use the power rule to take its derivative. So what we have is 1 over square root of 1 minus x times 1 over 2 radical x. Okay. I would be a very happy Mrs. Holman if you left it like this. If you wanted to simplify it all the way, let's remember our rules of radicals. Okay, the 2 is going to stay on the outside, but since we have 2 radicals that we are multiplying, it is okay to multiply what's underneath together. Okay, so you could write it like this. Two down, 2 to go. Questions on example 2? All right. Third example. Just for me to reference to you. Okay, this is the arcsecant derivative rule. Okay. So when we take the derivative, we have 1 over the absolute value of what? What did you say? Okay, which is what, Larry? Good. times the square root of, instead of x squared, we write 7x squared plus 1 squared. Are we finished? Times what, Abram?
14x.
Times 14x, because we have to apply the chain rule. Do not multiply this out. That is a waste of your time. Okay? Also, since 7x squared plus 1 is always positive, you wouldn't necessarily need to keep the absolute values there. You could treat them as parentheses, but it's better to be just safe and keep them there. Yes?
We don't have to find like the derivative of the whole denominator. You just take it with like.
Yeah, it's just chain rule. Derivative of arcsecant was this times the derivative of the inside is that. All right, example number 4. Besides having to use the arc cosine rule, what other rule are we going to need to use? The product. So how about you take a minute and see if you can write out the derivative for this product. And then we'll compare. Oh, and it's Pepper's scheduled today.
It is.
So we're out of here at 48.
What class is it really after?
3rd. All right, so Joe, what do you have?
X squared times -1 over square root of 1 minus x squared. And then plus 2x arc.
That's what Joe has. Do you agree with Joe? If you have these two flip-flopped commutative property, it means the same thing. Abram Cole looks like you had a question.
No, we got that.
Okay. So I would probably rewrite this as -x squared over radical 1 minus x squared plus 2x arc cosine. Bugs over here. And that's it. No. Okay. Now I've had some people ask me the past week, what is the point of derivatives? Okay. We have to learn how to take derivatives so we can apply them. Our entire rest of the semester is going to be about applying derivatives. How do we use derivatives to help us with other things? Okay? So hang tight through next week, and then we'll get to start using derivatives to work on problems that are a little bit more applicable, I guess you could say. Okay? So your homework is on your gold sheet. We have 10 minutes left of class. Let's get to work.